So do you want to summarize where we were after last time? We got stuck, essentially.
Sure, yeah. So we were talking about push-ups, and we came up with a very intuitive, or we talked about what our intuitions were for how the physics were going to work out for a push-up. Meaning it's going to depend on your angle, and it's going to vary somewhere between like your full weight and half of your weight, I think is kind of where we landed.
I think it was none of your weight, half of your weight, and then all of your weight.
Right. Yeah. And then we went through and we did some physics. We wrote out some equations, looked at some torques, and we both fell into the trap that the angle disappeared. We had a cosine of the angle and another cosine of the angle, and it divided from both sides. And and then that just didn't match with any of our intuitions. So we had to kind of stop and scratch our heads and really think about it.
Yeah. We started with just the conceptual explanation of how much weight you're lifting when you do a push-up, and then try to get into some force diagrams and torque diagrams. And writing everything out, we expected something to have angle dependence and come out, like we were conceptually explaining. But when we wrote it out, both of us hit the same issue that the angle just drops out of the equation completely, and it doesn't depend on the angle, at least the way that we set it up. So we were stuck. We didn't know why. So yeah. What headway did you make, Zach?
Right. So the only conclusion I think we could have drawn is that our model was wrong.
Right.
So I was trying to figure out what's wrong about our model, and I did some few things, and I think I came upon the main thing that we missed just recently, actually, and then I'll talk about how to kind of expand that to be a little more right.
Mm-hmm.
So the main thing that we missed is we were treating this like we had two concentric circles, let's say, and the inner concentric circle would be like where our body mass or our center of mass location is as a function of angle, as we rotate around our toes.
Mm-hmm.
And the outer circle would be like either your head or your shoulders or some part of you.
Mm-hmm.
And we were looking at how, if you change your angle, both of those change by some amount, but the pivot arm, the distance on, let's say, the x-axis stays constant, or the ratio of the two, of the center of mass pivot arm and the moment arm, lever arm.
Mm-hmm.
I forget what the right term is. And your shoulder, let's say, the ratio of those two things is constant. And if you think about it, for two concentric circles, that's exactly the case. And so the angle would drop out.
Right.
And so what I realized after I did a lot of push-ups, I looked at videos of push-ups.
I did the same thing.
And I think I realized the biggest error that we were making is that little model that I just discussed. There's a distance that's changing there that shouldn't be changing. The distance between your toes and your hands, like where your toes are touching the ground and your hands are touching the ground, that distance never changes throughout a push-up.
Right.
And our model treated it as though it was. So the second you fix that distance, now you're only talking about the center of mass moving on a circle, and the other distance just constant.
Mm-hmm.
The other pivot arm just stays the same. So then, therefore, you will get an angle dependence.
Right.
And I sent you this link to a Desmos plot.
Okay.
That shows you, so the first one, I don't know if it's drawn for you or not, the first NH, it should be orange when you look at the plot.
Mm-hmm.
That's, right now, the parameters are set up for my body. But that looks like, okay, great. We have like a cosine function, and it's kind of doing the thing that we want. The only issue still here is when you go negative distance. So what this is actually plotting, let me try and be a little more precise. Like if you, while doing a push-up, if you drew a horizontal line straight out from your shoulders,
okay,
the angle between your body and that line is the angle this is talking about. So when that angle is 0, you're flat.
Oh, okay.
So that would be the most weight.
Right. So it's a horizontal line, like parallel to the floor, and it's just at shoulder height when you're flat on the ground.
Yeah. The 0 angle would just be meaning that, you have, your body is parallel to the ground.
Got it. Okay.
So that's the point where we said, okay, that should be roughly half the weight. Well, okay, that's only true if your center of mass is exactly in the center of your body, but it's slightly off from that. And that also doesn't take into account your head necessarily. But yes, the point is that should be the max, or well, it shouldn't necessarily be the max, but that's the highest of the positive angles. So as you increase your angle, that means you're pushing up and it should go down, which is what you see here.
So the force
in the
starts at
plot.
its highest value and decreases.
Right. But we both said as you go into negative angles, meaning your shoulders are now closer to the ground than your heels are, it should be more weight. And this function doesn't capture that. It says it should be less weight.
Now I see it. It kind of goes up a little bit, but then it like there's a peak in some negative value, right?
No, I think you're looking at the red one.
Oh, then I don't see an orange one.
You got to click on it. It's one at the
first one up at the top.
Yeah.
Yeah. Okay, I see it now.
Right. Okay, so that function doesn't capture it. There we go. Okay. So,
sorry, I spoiled where we're headed.
Yeah. Well, it's a good segue into it. So the reason that doesn't capture it is because this model that we're talking about doesn't include your foot. It assumes that like you have just nubs at the end of your feet.
Okay.
So when you include your foot into this, what happens is as you do a push-up, and I'm assuming that the angle between your foot and your leg always stays 90 degrees. Maybe that's a slightly bad assumption, but that's what I started off working with. As you do your push-up, your feet actually go back. You know, your heels will go behind your toes.
Very slightly, but it does happen.
Yeah. And actually, you know, like if you imagine like, you know, standing up, you're entirely behind, you know, it's the length of your foot is the max distance it could be behind your toes. So it goes from being at the same point as your toes when your body is horizontal all the way to the length of your foot. It's the range there. And so, but that backwards motion pushes your center of mass just slightly closer to your feet. Or if you go down lower, you go to negative angles, your shoulders are closer to the ground. It pushes your center of mass further from your feet now, because it's now your heels are sticking past your toes.
Right.
And the closer your center of mass is to your hands, the more weight on your hands.
Right.
So when you include your foot, then you get this function in red, which is the next one. Notice it crosses the zero axis at the same point, but as you go deeper, it will then still increase your weight up to a certain point. Now, I think that point is probably due to the limitations of the exercise, meaning, you know, eventually your shoulders are going to hit the ground.
Right. And
also, like, as you do a push-up, at some point, the angle is going to, the way that you're pushing with your hands is going to change.
Okay.
So this is the best I came up with. It's not perfect, but I think it's closer than what we got. And it describes a lot more of the intuition that you and I came up with.
Why is there a peak at like negative point, I'll say negative 0.2, maybe negative 0.25, but then it gets less when the angle gets more negative from there. Do you know what I mean?
Yeah,
I would have thought it would have like monotonically gotten more and more as you decrease the angle.
Right.
Why does it peak and then go back down?
Yeah. So that I'm not 100% sure on. I think like I was trying to say, I think it might be a function of the physical parameters of your body, like because this is taking into account your foot, your body length, your shoulder, the distance between your hand to toe. Yeah, let's see. So like W is your weight, L is the distance between your hand and your toe, M is the distance between your heel to your center of mass, F is the length of your foot, B is the distance between your heel and your shoulder.
I don't see B anywhere in here. I mean, I see it defined as a variable, but it's not in either of the equation.
No, it's not actually used.
Oh, it's that purple line or something.
Yeah, it's used for that purple one, which we can get into, but I don't know if anyone would want to listen to us talk about it because it's more of just a function to check things.
So you showed me kind of this a while ago, like not all fleshed out, not in Desmos, not the complete equations, but just a sketch. And you did kind of explain where you were heading. And just before we started recording, I drew 4 quick sketches. One with your push-up, a horizontal push-up on the ground, like a normal push-up, and then with your head close to the ground, and then extend your arms up, right? Like just a normal push-up, low and then high. So that's 2 different drawings. And the center of mass when you're low, I said, was close to your hands. And then when you do a push-up, you're exactly right in that the distance between your feet and your hands don't move, but the amount of your body overhanging past your hands, like moving away from your feet, you reach your hands and then keep going. The amount of your body that's past your fingertips is more when you're at the lowest point,
right,
than when you extend your arms and go up. And then that means the center of gravity is closer to your hands when you're at the lowest point than when you push up at the highest point in your push-up.
Right.
So
sorry, I think I know where you're going with this. Maybe.
I guess my question is, do we even need the feet? Like, can we just say that this is how it works, and that's why when you're low, you're holding more weight than when you're high in the push-up?
Well, yeah. So I mean, that's that first function, the orange function there. That's the one that's just saying, yeah, it's going to increase, or it's going to be a function of angle, essentially, is what that's saying. And that's because exactly what you're saying, like, your center of mass is getting closer to your hands. You're having more mass hang over past your hands. Like if you watch a video of someone doing a push-up, you'll see when they're in the up position, usually you start with your hands directly beneath your shoulders. But as you go to the down position, your shoulders now extend beyond your hands.
Right. Yeah, that's exactly right. I saw that. Yeah. If anyone wants to see this, a good quick way to see a bunch of people doing push-ups is to go to Google Images and search push-up and then change the type to animated. And then you see a bunch of GIFs of people doing push-ups.
Nice.
That was how I took a quick survey of what it looks like. So my other 2 drawings were what I learned was a decline push-up with your feet higher than the rest of your body.
Okay.
And when you're in the low position, again, your center of mass is close. I guess it doesn't make a difference. And that was the problem, right? It's the same. Basically, it doesn't matter if your feet are higher than your body.
I'm kind of looking at your question here. I think we're going along the same lines with, okay, why does this peak at some negative angle? This plot for my body is saying it's around negative 12 degrees is the peak weight, or the peak of the amount of mass that'll be on my hands, or force, I should say, not mass. So the reason it goes down from there, I think, is because if you imagine, and you can just take away the feet for this if you want, why would it go decrease on the other side? Is if you don't have feet, right, you just have stumps again, then or you do it with your knees, I guess. As you pass, let's say you could pass through the ground somehow. I don't know. You look at, you're doing it on a mirror or whatever. It's going to, your center of mass is going to start moving closer to your feet again as you go past that point.
Okay.
So because your center of mass is moving closer to your feet, it's going to decrease the amount of force on your hands. So actually going negative in terms of this very limited sense where your toes or your knees are acting as like a pivot point and you can only rotate about that point, then it makes sense to me that it will lessen because you're now redistributing your mass so it's closer to your feet.
Okay.
Does that make sense?
I think so.
Like, just imagine, doing a push-up on with a mirror. The mirror should pretty much reflect, what's happening as you go into the negative space. And so it should be exactly about the ground that you're getting this shift.
Then how come we don't see that when we do like a 90 degree, when it angles 90 degrees, I guess negative 90 degrees, we're not lifting our entire body weight?
That's a good point.
Because that's what we expected to see. It's like it would keep getting harder and harder as we went closer and closer to 90 degrees until we were lifting, like we were doing a full body push-up, like a handstand push-up.
Yeah, I think it's just a limit of the model, because this is assuming, I think the issue is that it's assuming that your hands and toes are on the same flat surface.
I see. Okay, so we're not capturing the decline push-up with this.
Right. No. This is just your standard I'm on flat ground push up.
Okay. Then I believe this. Now I believe this.
Okay. Yeah, because I think if you're doing your decline push up, there's you do have a constant distance that's fixed in there. That's just not captured in this. My main goal was to figure out where the hell the angle went. Right.
I see. Got it.
And in terms of like accuracy of this model, so I took a more precise push-up force plot, but essentially I start out and it's around 700-ish newtons. Remember, I weigh 1,000 newtons.
Mm-hmm.
And then when I go down to my lower position, it goes to around 750 roughly. And I don't know what angle. It was just me by myself. I didn't have another person there to measure how far I actually went down.
Mm-hmm.
But so 700 when I'm at my upper position, and then this is saying 750 when I'm at my lower one. So if you just assume that I can do a good push-up, and I don't know that I can, this little model's predicting at my lower end of my push-up, or at the bottom position, I'll be doing like 810 newtons of force. So it's not exact, but it's close.
Yeah.
And it's 5% off. And then, that's what this other plot here is for, is to figure out numerically what the angle would be for my upper body position when I'm in the upper position.
Mm-hmm.
And I think, let's see, that says A. Okay. And then, so if I go to, I'm looking what it's saying for my upper body position, 750 newtons. And I was measuring about 700. So I guess there's a delta somewhere of around 50 newtons. But so not awful. It kind of agrees with calculation to some amount.
Yeah. And I think maybe a short answer for the decline push-up with your feet higher is, imagine like being horizontal, like with your arms on the ground and your feet on some bench or something like that, and then raise your feet higher and higher. Your body starts to adjust by having your center of mass get closer and closer to where your hands touch the ground.
Right.
And then imagine you have a force on your feet and a force on your hands, and your center of mass is at your hands, like at that location, if that makes sense. Like imagine a board with two upward forces and the weight somewhere in the middle of it, and then slide that weight towards one of the forces, the place where the force is acting upwards. What's going to happen is that force that you're sliding the center of gravity towards approaches the weight itself, and the other force tends to zero as you do that.
Right.
Ignore push-ups, just a horizontal board, and just slide the center of gravity towards one of the places where the force is acting. That force is going to be equal to the weight exactly when the two are on top of each other. So I think what we're saying here is that as you do a push-up or you're doing a decline push-up, your center of gravity approaches the place where your hands are holding you up. And as you approach that, the force of your hands increases until it's matching your weight exactly when your center of gravity is above your hands, as you would expect. Then you're doing a handstand push-up. Your center of gravity is directly over your hands.
Right. Yeah. So that's essentially what it boils down to. Mm-hmm. Is it's how close is your center of mass to your hands.
Right.
And I think the original question was like, what percentage of your body weight are you doing when you do a push-up?
Right.
And really, based on kind of this model that I've created, it really depends on your technique. You can vary it quite a bit by changing your arm's location. Right. Or the distance between your toes and your hands, or if you're doing the decline push-up, that'll just instantly put you into a larger force amount, So I guess the thing that I learned is just if you move your hands when you're doing a push-up further away from your feet, you'll be doing less weight.
Yeah, that's right. I mean, obviously your body, there's limits to that. Like if you stretch your hands out in front of your head, you're not going to be able to do a good push-up.
Right. Well, you'll be lifting less weight still. It's just you're using a different muscle group. Yeah,
and we're not getting into anything like that, like the physiology of the body. Yeah. So I was thinking about this when I was working out. I was doing like a chest day, and the warm-up was push-ups. And I was like, well, why am I warming up with push-ups? That seems excessive if I'm going to be like bench pressing not much weight, 40 pounds. I'm like, well, my push-ups are much more than 40 pounds as a warm-up. Like, why don't I warm up with like 5-pound lifts? I don't know.
Yeah, I mean, I guess rough estimate for me is it's somewhere between 70 and 80% of my body weight, which is,
more than 40 pounds.
Yeah. It's quite a lot more.
Yeah. I guess I don't know. I don't know what I'm doing when I'm lifting weights in like a bench press, like laying flat on my back and pushing weights up. In my head, it's the same thing as a push-up, but I guess probably not.
Yeah. I feel like it's similar. Yeah. Physiology, I don't know. One thing I thought was interesting about this question is, I didn't spend a whole lot of time, but I did a fair amount of Googling trying to just find the answer. Or I looked, through some journal databases at the university, and nothing super easy to find, at least, came up that was here's the physics of a push-up. So
right, exactly. Yeah, same thing. And I even found like a physics stack exchange thread. Someone asked the exact same question. There was no satisfactory answer that I saw. So let's publish.
Yeah, seriously. I want to do a more detailed measurement one day, but not today. Okay, well, I feel like we've covered push-ups pretty well. Hopefully, people have a decent understanding. It matters your angle, and the real important thing is how close is your center of mass to your hands.
Yep, there it is. Cool.
So what's up for today? What's the next week's thought?
The question is asking, basically, in so many words, this person was asking, why is geosynchronous orbit where it is? Like, not why is it that number, but like, why is it a specific place? Like, why can't you put a geosynchronous satellite at any altitude above Earth? Like, why does it have to be an exact altitude?
Okay.
So, do you know why?
Well, I think before I take a guess, maybe we should talk about what a geosynchronous orbit is.
Sure. Lay the foundation. Yeah. I can explain it. It's just the Earth spins around once every about 24 hours. So a satellite that's geosynchronous means that it's also going around once every 24 hours. So it's always fixed above a particular point on the Earth, and it just spins around or orbits around the Earth. And yeah, if you work out the physics, there's a particular distance from Earth that these satellites have to be in order to do that.
Right. So it's like if I'm in Santa Barbara and there's a geosynchronous satellite above me, I can always look up to that same spot in the sky, and that'll be there, whether it's noon or midnight or any time in between. Right. Okay.
Yep. Yeah. So I guess a few points before we get into the answering of the question is it's interesting to think about what place on Earth are these things directly above? Like, where on Earth, if you went from the center of the Earth to the surface of the Earth and then to the satellite, like where would that be a complete straight line? Do you get what I'm asking?
What I heard was 2 points, which is always a straight line. So what am I missing?
No. Okay. So there's 3 points. Center of the Earth.
Yep.
A point on the surface of the Earth, which I'm asking, where are those points? And then the satellite itself. So if you went from the center of the Earth to the North Pole and then the International Space Station, that's definitely not a straight line, right? Unless the space station happens to be passing over the North Pole at that moment.
Right. So it's like kind of where can we have these geosynchronous, like can we have it at any latitude or...
Right, like you said, Santa Barbara, like is there a geosynchronous satellite that goes directly above Santa Barbara at all times? Like if you looked straight up.
Yeah, I don't personally know, but I don't I don't think so. Yeah, so I'm imagining in my mind, at least for a given height, it's equatorial. Maybe it could be, I want to say it's, okay. Because the other orbit I'm imagining doesn't exist. So I think it's an equatorial plane, right? It's got to be like at the equator level.
Exactly. Yeah. So all the geosynchronous satellites are geosynchronous over places on the equator. And so in Santa Barbara, you look up in the sky and there are geosynchronous satellites. I mean, I shouldn't say directly up in the sky, but you look somewhere, you point your satellite dishes, like all the television satellite dishes are pointed at geosynchronous satellites because they have to always point towards the source. It's not like the dish on your roof is rotating them to like match where the place is of the satellite that gets the television signal. So your dish always points towards essentially geosynchronous satellites that are over the equator.
Right. Okay. So it's like I can imagine a situation, I don't think this exists, but I can imagine a situation then where if I was on like the North Pole, let's say, or I don't know if the North Pole exists anymore, so I'm going to say the South Pole because that's a landmass.
Okay.
You're at the South Pole, you might not be able to see it if it was like, I'm just going to pose a stupid satellite. If it was, 6 feet off the ground, like you couldn't have a line of sight to that satellite. But if it's really, really far away, like moon distance, right? You can see the moon from, I think, from the South Pole, from anywhere.
Yeah, you can see over the curvature of the Earth. Like you can see over the horizon.
So I think I'm guessing then that these satellites are high enough that you can see it over the horizon at any point on Earth.
That's right. Yeah, and you can see about how high over the horizon they are if you look at satellite dishes on your TV. And like if you ever set one up, it tells you like where to point the satellite, and like it like tests for signal strength and you adjust it. But if you're in Santa Barbara, which direction do you think it points? You probably know.
I mean, it's south.
Yeah, it's always pointed some general south the direction. Yeah. And then if you're like in Australia or South Africa or something, you're going to be pointing those satellite dishes north to capture the signals from the geosynchronous satellites.
Right. And so here's the reason I said it's got to be over the equator, is I imagined it being over, like, let's say it is over somewhere in Canada, like at all times. The orbit that would be making is if you drew a line from let's go to the geosynchronous one. If you draw a line from the center of the Earth to the satellite and you sweep that out over its orbit, it forms like a disk.
Right.
But if you did it with like a place over Canada and you connected the line between the center of Earth to the satellite that's over Canada and you spun it around, it would form a cone.
Right. Exactly.
That doesn't work.
You can't orbit around.
Yeah, you have to orbit around the center of mass.
Right. Yeah. So a circle that's like if you sweep out the line makes a cone. We don't get orbits like that. Like you don't get little halo orbits around.
Yeah. That's a good way of putting it. Yeah, it's not a little halo. Yeah, definitely. Because the center, there's no object. You have to be going around the center of something, the center mass.
Right. So. And you could make that disk, you could have it over Santa Barbara at one point or over Canada at one point, but that sweeping out of the disk for the geosynchronous orbit over Canada or somewhere not on the equator, it would be at an angle. So like it'd be like taking a sword slice through the globe at like an angle, not through the center of, like not through the equator.
Right.
Yep.
Yeah. Okay. All right. So, geosynchronous is a satellite that is constantly over some point on the equator at all times.
Yep. So if you were standing at one of those places and looked up, there would be a satellite there all the time.
All right. Okay. So the question is now that satellite has to be at a particular height.
Yeah. So why can't we have? Well, I won't use your 6 foot analogy, but in theory, if something like the moon or Mars, where there's no atmosphere, or some barren planet or something, we could put something at 6 feet and have it orbit the planet.
Very smooth planet.
Yeah, exactly. No mountains, nothing. So why can't it be at 6 feet? Or why can't we have a geostationary, geosynchronous orbit like at the altitude of the space station, which is not very high? And these geosynchronous ones, let me get the number. The guy asked the question like 35,000 kilometers. So we're talking like tens of thousands of kilometers. Whereas the space station, I think, is just like 100 kilometers, couple hundred kilometers, not very far.
So, okay, let me look something up real quick because I was reading all about orbits because I thought we were talking just general orbits.
Well, we might actually. So a part where my explanation might fall flat is when I get into like general orbits. So I might need your help there.
So I think this is well, I'm looking on Wikipedia and it's saying it is oh, well, okay. It has its own classification. I was looking at like all the orbits. There's like low Earth orbit, which I think is what the ISS is.
Yeah.
And then it says medium Earth orbit, but it also says Molniya orbit. Maybe those are two different. I don't know.
Huh.
And then, geostationary actually is its own class of orbit. And then above geostationary is the high Earth orbit. So it's saying
we should say, just before we get into this, we should say that you can orbit at any height. It's not going to be geostationary. That's the problem.
Right.
Like you can be in a circular orbit at any radial distance from the Earth.
Right. Yeah. Right. I mean, if you go to you get rid of all the air, you go to the Mount Everest, and you shoot a ball fast enough off of it, it can orbit at that height, 10 feet above Mount Everest.
Mm-hmm.
Yeah, or you can go even super far, where you have things like Halley's Comet, which goes like ridiculously far away and comes back.
Right. But that's an elliptical one, and I'm trying to stick to just circular, which we might need to get into elliptical in a bit. But yeah, circular orbits, you can get a circular orbit anywhere. Yeah,
so Wikipedia is saying geostationary orbits are 42,000 kilometers on the nose from the center of the Earth.
Okay.
35,789 from the surface.
Okay, cool. So altitude of like 35,000 kilometers.
Right.
35 megameters. So why is it that height? And we can kind of reframe the question a little bit and just throw out a fact and talk about why this is true, that for any given radial size of a circular orbit, or any orbit, the period is uniquely defined for that circular orbit. Do you get what I'm saying? Like the second you know the radius of your orbit, you know the period. You know how long it takes to go around the orbit once.
Right. Yeah.
Like those are one-to-one pairings, like unique. One fixes the other one.
Right. Yeah, exactly. And I think that's kind of the whole crux of the problem there is, if you need it to be, you need the speed to match that of the Earth. Mm-hmm. And so since you have this one-to-one pairing, you need the speed of the satellite, the angular speed, to match the angular speed of the Earth. So if you have this one-to-one pairing, then your height is just immediately fixed,
right,
to 42 or 35,000 kilometers.
Mm-hmm. That just happens to be the distance that gets you a 24-hour period.
Right. So I guess we can say that, but I think the question really is, okay, maybe a little deeper than that would be, why is it this one-to-one pairing?
Mm-hmm. Exactly. So my attempt at an explanation was to use an analogy of a ball on a string.
Okay.
And that's the satellite. And ignore gravity, but just imagine the tension in the string. So imagine you're spinning around, like, I don't know, in the middle of an ice skating rink or something. Just you have a huge open field and you're free to just spin with a ball on the end of a string.
Mm-hmm.
My question to you is, so the key point of all of this is we're fixing the amount of time it takes for you to spin around once. Probably not 24 hours, because that would take a really long time to spin around. But just any sort of comparison, just remember we are taking the same amount of time to go around the circle.
Right.
So is the string at a higher tension when it's close to you, or is the string at a higher tension when the ball is far away from you? Like when the string is short or when the string is long as you spin around in a circle?
I don't have an intuition for this, and I don't have the math off the top of my head.
You're allowed a free body diagram.
All right. So, okay, here's what I'm in kind of intuiting.
Mm-hmm.
A little bit of algebra. So, okay, the thing I was missing, you just gave me the warning, and I heard it, I absorbed it, and it immediately fell out of my head until I realized again. Okay, so the thing that's important between these two radii that we're talking about for this ball on a string is it's taking the same time to go around for both of these balls. So then
exactly.
Well, okay, once you know that, then it's okay, which one has more tension in the string? And I think it's the longer one.
Okay. How did you arrive at that?
Okay, well, I remembered I alpha. Well, I alpha. So the moment of inertia times the rotational acceleration is equal to force, right? Torque. Okay. Ooh. Yeah. Okay.
Well, I can tell you right now that that's incorrect, because the thing is rotating at a constant angular velocity, so alpha would be 0.
Right. Okay. I'm trying to remember what angular acceleration. Okay, wait, no, but okay, that's 0. Damn it! What is the equation for centripetal force? mv squared over r.
Yep, that'll work.
Okay. All right. Well, yeah. Okay. So then it's the exact opposite of what I said. But I'm not seeing it intuitively in my head or through a little picture. So what am I missing? Help me out.
Well, if you went down the v squared over r route, you'd get in a bit of a pickle with the v changing as you change the distance. Because if you went around a small circle in 20, or let's use a realistic number, like say it takes you 1 second to spin around in a circle.
Okay.
If the circle's small, the ball on the end of the string is going to be moving pretty fast to get around that circle. Sorry, it's going to be moving pretty slow to get around that circle in 1 second.
Right, because the circumference is really small, so it doesn't take...
So imagine your string length is like a meter, and then stretch the string out so it's like spanning... I don't know why I'm on an ice rink. Friction doesn't matter, but in my head I'm on an ice rink because it's a physics problem. So imagine you're on the ice rink, and the string is like as big as possible to fit in the ice rink, and you still go around in a second. That ball is going to be moving real fast, right?
Right.
So now you got R and V both changing in a not straightforward way.
Okay.
So the simpler way to think about it is the other form, instead of V squared over R, is omega squared R.
Okay.
Does that ring a bell? Instead of V squared over R, you have omega squared times R. And you can work those out going between them with V equals R omega.
Okay. Yeah. All right. Yeah. Okay.
Yeah?
Yep.
So I'm imagining like a Newton's second law thing with the force being the tension in the string, which I'm asking about now. So which is the higher tension, a short string, in other words, a small circle, or a long string, a large circle? And you have the tension equal to ma. The only force is tension working in the radial direction of the circle. So that's equal to ma. And then we said A was equal to omega squared R.
Right.
Or if you wanted to, you could work it out with V squared over R, but just be careful. You're going to have to convert anyway.
Right. Well, yeah, because omega is the angular velocity, and we're saying that's constant. It's 1 second to go 360 degrees.
Yep. So, and if we want to go between time, meaning the period, and omega, we got to use omega equals 2 pi over the period. But that doesn't really matter because the key thing is that omega and the period are both constant.
Right.
That was my whole big hint.
Yes. Okay. So yeah.
Omega's fixed, and we have T, tension, equals M omega squared, which are both constants, times R.
So, okay. Yeah. So the larger one then.
Yep. Tension is proportional to the radius in this example, right?
Yes.
So if it's a short string, a small circle close to you as you spin around, you're going to have a lower tension than if it was a long string and you're spinning around in the same amount of time. That string is going to be pretty taut because you got to get that ball around the circle in the same amount of time, but it's got a much larger distance to cover.
Right. Okay.
Good so far?
Yep.
Okay. So close, weak string, far, strong string.
Right.
Okay. If gravity was like the tension in the string in that we could adjust it to be whatever we wanted, if we wanted an orbit that was geosynchronous, meaning it took 24 hours to spin around, and we could adjust the strength of whatever force was causing the satellite to go around in a circle, perfect. We could bring it into a tight circle right above the Earth, swinging past the space station in 24 hours. Mm-hmm. The problem is we don't have a string connecting the satellites, keeping them spinning in a circle. We have gravity, which behaves not like a string. We can't adjust gravity to whatever we want.
Right.
So again, to recap, tension is low when the string is short and high when the string is long.
Right.
So how about gravity now? Is gravity when you're closer? So now imagine orbits around the Earth. Is gravity stronger when you're close or stronger when you're far?
It's stronger when you're close.
Yep, right. So we got the inverse square law for gravity. So it says if you're close, gravity is going to be strong. The two objects attract each other if they're closer together.
Right.
And if they're far away, the gravity force between them is going to be pretty weak. So we have these two kind of opposing, I guess, or I guess contradictory ways of thinking about spinning in a circle. With the string, we could adjust the force to whatever we need to get a circle to happen at a particular amount of time. But for gravity, we don't really. And gravity is the opposite. If we're too close, gravity's too strong. It's stronger than the string tension that's required to keep it spinning in a circle.
Right.
And if we're too far, gravity's too weak to keep that satellite spinning in a circle at the fixed time.
So if we're too close, it's too weak, and we're just going to fall and hit the ground. Or sorry, too close, it's too strong. Sorry, just said the opposite. If we're too close, it's too strong. We're just going to fall and hit the ground.
Right.
If it's too weak, like really weak, we're just not going to orbit at all. We're just going to go off on our merry way. Mm-hmm. And nothing's going to, we're not going to have an orbit. Right. And then in between there are actually two states. There's the circular orbit and the elliptical orbit, but we'll just focus on the circular.
Yeah, stick in the circle. Yep. So there's a kind of like Goldilocks perfect distance where gravity is just the right strength, meaning if you adjust the tension in a string and you had some ball spinning around taking 24 hours to spin around, the distance where gravity equals the tension in that string is going to be at that 35,000 kilometers height above the surface of the Earth. Does that make sense?
Yeah.
So
what's wrong with your analogies?
I don't know.
You're asking.
And maybe it's too convoluted. Like, why'd I have to introduce another force that didn't really explain the first force? It just kind of put a different mental picture in your head. I don't know that it explained it, but it was fun to think about and like go through it.
Yeah, I mean, I'm following. I think it makes sense.
Yeah.
I mean, at least it makes sense to me.
I added a little bit, and I said, if the string was as strong as gravity is when the satellite is closer, like if you pulled harder on the thing, yeah, like you said, you'd crash to the Earth. And I think if you're trying to keep it spinning in a circle, it wouldn't go into elliptical orbit. I didn't get into any of that. I think I said it would spiral into the Earth because it's trying to move around a fixed amount of time, but the force is too strong. So it's kind of like spiraling into the Earth.
Right.
And then if it's too weak, it would spiral out away from the Earth. Like it would still try and go in that circle, but it's just not strong enough to keep it moving in the circle. So it would kind of start to, your string is too weak. You start like getting slack in the string, and it's like pulling out the string as the ball moves further and further from you because you're not pulling hard enough.
Yeah. There's also another orbit, if you will, that we didn't mention. I just want to make sure we cover everything. Mm-hmm. Isn't there's hyperbolic orbits too, right?
Yep.
I don't know the details off the top of my head, but
hyperbolic is when you're moving too fast and you're not actually bound to the planet. So you're coming in too hot and you're just going to like slingshot away from the planet.
Right. Okay.
If you look from above, now I don't remember my basic geometry. Whatever the little point is it the focus? I know it's that for parabola.
I think it's the focus, yeah.
For the hyperbola?
Yeah.
So the planet would be at the focus of the hyperbola, and the orbit, quote unquote, the hyperbolic path is like swinging back behind it. That's your little hyperbola.
Okay. Yeah. So I think, here's the thing I kind of thought of as you were explaining your analogy, that you can either tell me if you think this will make it easier or worse. Mm-hmm. But have you ever had one of those like janitorial key rings where it's like you clip it on your belt and you and it unlocks the door and you let go and it goes back to your thing?
Yeah.
Have you ever spun the keys around on one of those?
I don't know what you mean. Like, I'm imagining like
you let out some amount of the line.
A guy in a zoot suit, and he's like leaning up against the wall and kind of spinning his chain or something. Is that what you mean?
Yeah, exactly. Except know it's one of those retracting key rings.
Okay,
that sucks it back. Mm-hmm. And so have you ever spun that thing?
Like you have the retractable part in your hand, and it's able to stretch and retract freely, but you keep it spinning in a circle.
Yeah.
I can imagine that. I've never done it, but I can imagine it.
Yeah.
It sounds pretty fun.
So it's I have one of those on my person every day. So I do this when I get bored. But I think this is actually almost exactly kind of what's happening is, take the exact scenario that you've said, and it might not be mathematically equivalent, but to get a better intuition, I think it might be a little better is replace the string with a T with a spring with a P.
Yeah.
Because then when you spin the spring, and if you want it to be a certain distance away, you have to spin it at a certain speed. Uh-huh. I don't know if anyone's done this. I've done it. That's why it's so intuitive for me.
So you reminded me of something from my classical mechanics class. Like, I don't remember if it was like upper division, like junior, senior level classical mechanics, like not the intro, but we worked out orbits. And I remember if you had some force that went with some power law, like R to the N, like any power, there's two situations where you get closed orbits, closed paths. And I might be saying this wrong because it's been a really long time since I've done any of this kind of stuff. And what I don't remember if it was closed in real space, like spatial dimensionally closed, like a circular orbit is closed, like it ends up where it started, or if it was a closed path in phase space, which is like plotting position versus momentum. I don't remember what closed meant in this case, but it could only be closed in an inverse square law and a linear force. So only in like gravity or a spring, like a Hooke's law force, which is linear with distance. So I don't know. That reminded me of that, is that you can get a closed orbit with gravity or a spring. And again, I could be totally wrong on the details of that, but I thought that was an interesting fact when we learned it. Something to look up. Exercise for the listener.
Yeah, or more explanation for us.
Yeah. Yeah.
But
the keyword you want to look up, and I'm going to say it and not be able to spell it, so it might not be any help, is Lissajous curve.
Oh, yeah.
Lissajous. Yeah.
Those are fun.
Yeah.
Yeah. So I mean, because the problem with a string, I feel like, is tension is set by the mass of the object, at a given radius, fixed radius, by the mass of the object and the period, or the angular speed.
Right.
And so changing what am I trying to say? Changing the reason then I'm trying to think about your analogy. Changing the tension in the spring, like gravity changing, seems like a strange concept, or am I missing something? Because
I guess my whole point was ignore the string.
Okay.
In Newton's second law, for an object in circular orbit, you have gravity on one side of your F equals ma. So the F part is gravity,
right?
Which goes like 1 over r squared. On the right side, you have ma, which ends up being m omega squared r. So on the left, you have something that's proportional to 1 over r squared. On the right side, you have something that's proportional to r itself. And if you plotted those two plots, like a 1 over r curve and an r curve, they intersect at one point, and that's your circular orbit. That's your geosynchronous orbit for a fixed period. And so I was using the tension as kind of like the catch-all for everything on the right side, the m omega squared r, just to say like all of this is some term, call it whatever you want. Say y equals m omega squared r, and then say y equals gmm over r squared. And then the place where those two things intersect, plotting both of those y equals equations, that's your circular orbit.
Right. Yeah. I mean, I don't see an issue with your analogy.
I wasn't wrong. I just maybe overcomplicated it, which is why I got the downvotes.
Yeah. I mean, I don't know. I haven't spent much time on presumably the physics subreddit or the science subreddit, but I don't know how pretentious that crew is.
So I have like multi-subs where you just like group a bunch of them together, and I just go in there, and I don't even know what subreddit it is really when I'm looking at stuff or posting, because I just see the topics. I mean, obviously it looks different, but I don't really pay attention to which one I'm in.
Right. But yeah, I guess for me, the thing that seemed more intuitive was a spring, since it does have kind of a set force. Yeah. Like it is. Okay. So I guess that's what I'm trying to say is the difference between like a string and a spring. God, that's awful. Is that the spring, the amount of force from a spring is changing with the stretching or compression of the spring, whereas the string, it's not related to that.
Right.
And so that I guess that's the only non-intuitive part of your description, but following it along, I mean, I can follow each step of the way, and I understand exactly what you're saying. And I don't think that it's wrong in any ways. I mean, especially when the tension part of it was just to get you in the state of mind to deliver the final thing, which I think was, the right answer anyways. So like you could just started with that, and it would have been right.
Yeah. It wasn't like a popular thread. I don't even know why I'm dwelling on it so much. It's just kind of a funny like motivation to talk about this topic. I think it's kind of interesting. But yeah, the other people were like, just went straight into like the equations. I'm like, cool, that doesn't really explain why. Like, it's because it's a 1 over r squared force. Cool. What does that mean? Yeah.
So. It's a balancing act between distance and speed to some degree is kind of, how I see it. And it's only, each orbit, in order to meet that balance, has one point for it to be a circular orbit.
Right. So what's interesting is I'm thinking about, so I'm thinking of replacing the I'm going to say rope instead of string because it's easier to distinguish.
Okay, rope.
I'm going to replace rope, the tension, with a spring, like you were saying.
Okay.
But think of what that equation says. It says the spring force, which is, if we're using r for the distance the spring is stretched,
okay,
it's saying K times R, the spring force, equals m omega squared r, right?
Yeah.
So r drops out of that equation. If we wanted to find, like in the other case, we could solve for r because r was in the equation at the end, right? You could find what that distance is, plug in your omega, then you got your r, right?
Yep. Yeah.
But in the spring case, we don't. There is no r. But I see what it's saying, though. It's saying that your spring has to have a particular spring constant in order to be a circular orbit at that omega.
Yeah.
That's interesting. There's no distance requirement. There's only a spring constant requirement. Is that true? That seems not correct. I guess it's true.
Yeah, I mean, because with tension, we're just saying with the rope that it's tension, some force.
Mm-hmm.
We haven't gone into what that force is.
Right.
We just said it's a force. Whereas now with the spring, we could also just say, oh, it's a force.
Yeah.
But then now we've said, okay, we can describe this force via KR or KX or.
Yeah. I guess what I was getting at was with gravity, you could solve for a particular R, which I guess, so here's the answer to the question. Gravity, you solve for one particular value for R that defines the orbit at that particular omega or period, whatever you want to think about, right? Mm-hmm. The equation gives you one value for R. For the string, you can put any value of R because you can adjust the tension to whatever you want. So there is no geosynchronous orbit for if the force was a string, because it would just adjust. Like we said, you spin around with a short circle in 24 hours, it's going to be whatever tension it needs to be, and it's not very large. And then if it's a really big circle, spin around in 24 hours, you're going to have a larger tension. So you can have a circular orbit that takes 24 hours to go around at any radial distance if your force was a string. But what about a spring? Is there a particular distance, or can it be any distance? Or is it only dependent on the spring constant being correct? And the second you have the correct spring constant, then you can have it at any radius. Is that true? I want to make a ball on the end of a spring spin around me in 1 second. Do I need a particular spring to do that, or can I do it with any spring? And if I have the right spring, can I make it at any radial distance?
Right. Okay. So I think if it's I think if you have K equal M omega squared, mm-hmm. then it's going to be any distance?
I think that's true. Well, first of all, the math just straight up says it's true, but I'm trying to intuit, is that actually true?
Right. Okay. Well, all right. So if you imagine, let's say we have let's see if we can compare a really weak spring mm-hmm. to a really strong spring.
Yeah. I was trying to do that in my head. I kind of like your little retractable string thing better for the model, because I tried a car's shock absorber spring is my go-to of a really high spring constant spring, but that's already a fixed distance.
Yeah, that's a pretty much a rod unless we start moving crazy speeds.
Yeah.
Or we have a really big mass, I guess.
Mm-hmm.
But yeah, so I'm trying to imagine just like a trampoline spring versus, one of those conical springs that we use for the simple harmonic oscillator.
Yeah, a slinky.
Yeah, a slinky. There you go. That's even better.
Yeah.
Everyone knows a slinky.
Yeah.
Yeah. All right. What are we asking? You have to get back to that.
Can we, if the spring constant is correct, we agree that the math says that a spring constant needs to be equal to m omega squared. We want to again fix omega. Omega is constant, mm-hmm. and I guess mass is constant. I didn't really think about that with gravity or the string, but let's just make it so. So we have the proper spring with the proper k value to get this thing to spin around in a particular omega.
Right.
So does that mean that with that spring, we can have a circular orbit at any distance? So say the slinky is correct. I think it's true. And it's right. Whatever period and mass we have, the slinky is the right spring constant to get this thing to go around us in a circular orbit. And we stretch the slinky out to a foot, and we spin around in our time, however much time that is, 1 second. And then it stays in a circular orbit. We can go around and around in a circle once every second, and that slinky is going to stay exactly the same length. If we then stretch the slinky out to, 5 feet, stretch it, and then go around in the circle once every second, is the slinky going to stay 5 feet long? I think it is. Mm-hmm. 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 Right. Mm-hmm. Oh, I just realized something, and if any of my students are listening, maybe they caught this because I would always hammer it in their heads. Do you want to finish your thought? Sorry, I interrupted you. So, okay, let's ignore circular orbits. But whenever we teach springs and simple harmonic motion, we draw parallels to circular motion because a lot of the equations look similar. And we do the little demo with something spinning in a circle, and we shine a flashlight on it, and we show the shadow, and it looks like a mass going back and forth on a spring, right? Cool. Now, from simple harmonic motion, we know what does the period definitely not depend on? Depends on mass. For a mass on a spring, yeah. Squirt, yeah. That's your omega. But what's not in that equation? Yep, the amplitude of the simple harmonic motion, right? That doesn't affect how long it takes to go back and forth on the mass on a spring. So, I mean, going backwards from the comparison where we say, oh, it's just like circular motion, because we already studied that usually in the order we teach it. Going backwards, then it's the same thing. It's at any radius, you can have something spinning in a circle. I know it's not exactly the same, but at least there's a connection to be made that it's amplitude independent, which means instead of simple harmonic motion, we have uniform circular motion. Yep. Exactly. Yeah, so it's kind of, we're working at it from a weird angle of saying fix omega and m, and then we find our k, and then we get the k spring constant to be correct for whatever we need the period to be, and then we're good. So yeah, I think what I was saying, if you stretch it a foot, spin in a circle once every second, it's going to stay a foot. Stretch it 5 feet, spin in a circle once every second, it's going to stay 5 feet. Interesting. Geostationary or geosynchronous. Yeah. Mm-hmm. Right. Mm-hmm. Mm-hmm. Right. 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 Yeah, well, that was fun. I got one more puzzle, and it's a quick one.
Okay.
I meant to use it as an intro, but I forgot.
Okay, let's hear it. Yeah.
Somebody asked, and I had to think about it a little bit. I didn't reply, but I did read somebody ask, why can't the escape speed be 1 mile an hour? Like if you just had a rocket that you hit cruise control on and said, always make me go 1 mile an hour, why can't that just leap? Like, why is our escape speed so high? Like, why can't we just leave at 1 mile an hour?
Right. So it's like, okay, in a world where there's only the Earth and yeah, we have an infinite source of energy on this rocket, we send it away at 1 mile an hour. It doesn't matter how long we wait, whether it be, if we wait 10 seconds, it seems obvious, okay, it's going to fall back down to the Earth. But if we waited 1,000 years, so now it's God, I don't know how many hours are in a year, but stupid far away from the Earth. And then we said, okay, turn off the thing. It's still going to fall back to Earth at some point. Like we'll stop. Yeah. Right.
I don't think so, because it took me a second to think about that, and I went where you're going, but I eventually came to a different reasoning. And it's kind of it's not a tricky question, but the way it's worded, like I wouldn't ask a student this question because it kind of plays a trick on you.
Okay, well, yeah. So can you even accelerate, or not accelerate, but can you move at a constant velocity of 1 mile an hour straight up from the Earth?
I don't know. It didn't ask, could you? It just said, I mean, it's physically possible to. It's not like breaking the laws of physics to do it, but could you build something to do it? I don't know. Probably not. It'd be pretty hard.
Right. Well, okay.
Maybe like a space elevator. So I'm going to give you the hint, unless you think you got something.
No, I'm still at the point where my
So you think if you were, light years away from Earth and this thing was cruising at 1 mile an hour and you turned off the engines, it would fall back to Earth?
I mean, that's what I've been told. I've learned in physics is, provided, there's no other planets or anything in the system. It's just these two things.
But it's moving 1 mile an hour. It's not at rest. I agree. If things are at rest, like if things are stopped infinitely far away, the force of gravity extends infinitely far. If something is stopped and the only object in the universe is the Earth, wait long enough, those two things are going to collide.
Okay, all right. So let's maybe what I need to do is review. Okay, an escape velocity is the velocity it takes for something to leave Earth and never return back to its orbit.
That's right.
So, okay. All right. So let me see if I can talk through this for a second. This is where I was kind of, my question about the 1 mile per hour thing was coming into my head. That was bothering me. Okay. So yeah, I feel like it's an engineering answer, but so yeah, if I threw a ball at 1 mile an hour straight up, Earth's pulling on it and dragging it back down, it's not going to escape. If I threw it at, what is it, like 8.6 kilometers per second or something? What's
something like that, yeah.
On Earth, a speed of 11.2 kilometers per second. I think.
That's the escape speed?
Yeah.
Okay.
So yeah, okay. Then if I threw a ball at 11.2 kilometers per second, it's never coming back.
That's right.
Okay. But now if we talk about something moving at a constant velocity of 1 mile per second, there's some engineering solution to this. It's a rocket that's canceling out the force of gravity the whole time.
Right.
So yeah. So it is just going to move indefinitely. It could move away from Earth. Yep. Indefinitely. But if you turned it off, then the force of gravity is still going to suck it back at some point.
Even like wait years, like it's light years away.
Yeah. If you turn it off at that point.
See, that's where I disagree. I don't think so.
So, okay. Is that because, let me think. Okay. So now, all right. Now, okay. So the escape velocity depends on where you are in a gravitational well. So yeah, okay, if I'm light years away, at some point, the escape velocity is going to be 1 mile per hour.
Yep, exactly.
There we go. Okay. Yeah. So, and then, because now I'm just in a really weak gravitational. The other way to think about it is, I could be on a yoga ball sized planet and throw a ball at 1 mile an hour, and it's going to escape.
Yep, some rocky formation somewhere in the universe has an escape velocity of 1 mile an hour on its surface. And that's the key thing, is the escape speed is determined by the distance from the center. So we talk about it in terms of the surface of the Earth, which is a fixed distance from the center, essentially. So the escape speed of Earth is 11 kilometers a second. To leave the surface, and this is the thing that tripped me up, is understanding the escape speed is like, imagine like a quick impulse. Like it's just like this thing goes from 0 to that speed and then no more forces. Like it's off, and then it'll leave. Like you said, like throwing a ball or like hitting a golf ball, or in rocket science, they consider the rocket, even though it lasts for a while, it burns for a while, they consider it like an impulse. Like it's not on the whole time the rocket's flying.
Right.
They eventually want a rocket to turn off.
Yeah. And that's if you do that, you have to reach a certain speed from the surface of the Earth. If you were launching from the International Space Station, you were launching another object, you have a smaller potential energy that you have to outdo.
Mm-hmm.
because you're further away from the surface of the Earth, or the center of the Earth, really. So, right. Yeah. So then the escape velocity from that point is less, and it just keeps getting less and less as you go.
Right. Yeah. So at some point, imagine the Earth, same mass, but an Earth that's the size light years radius or something like that. A huge Earth, but the same mass. At some point, the size of the Earth gets to the point where the force of gravity pulling from the center of this light year radius planet is weak enough that you could jump off at 1 mile an hour and leave.
Yeah. Right. Yeah.
Yeah. So that was a kind of weird question that tripped me up for a second. I was like, wait a second, why can't we do that? Why is the escape speed what it is? Why isn't it any speed? You can just escape.
Right. Yeah. Yeah. Because if you keep adding, you keep a constant velocity, you can escape whenever you want. Well, provided you give enough time.
Right. It's also funny to imagine a little rocket ship going 1 mile an hour and just going off forever. So to finish up with some fun facts, you said the space station, the gravity's weaker.
Yes.
And your escape velocity, if you launched something from the space station, would be less because there's less gravity, the weaker force of gravity.
Yes.
So this is a fun thing I used to talk about with students. So it's weaker, but it's not that much weaker. Like the people are weightless, quote unquote, not because there's no gravity.
Because they're falling.
They're falling, right. The whole spaceship is in free fall around the Earth, orbiting in a circle. So the space station is pretty darn close. And the fun fact is that as the space station passes over Sacramento, California, the space station is closer to Sacramento than the Pacific Ocean.
Wow.
It's pretty close. It's like, not that far, like 100 miles or something.
That is pretty cool. Wow. Yeah, which really just like shows you like how close we really are, in that. But then it's also like at some point is so mind boggling that we put someone on the moon at the same time,
right. Yeah. The comparison, if you do like proportionalities with the globe, that's like picture a globe the size of a basketball, like a normal globe. I guess that's a little bit bigger than a basketball. But if the Earth was the size of a basketball, how far would the moon be?
God, I have no idea.
Like guess, like is it like across the bed? I'm looking at my bed, so I'm trying to find things like, is it like globe on one side of the bed, moon on the other side of the bed, or is it like across your laptop?
If I had to guess, just intuit a distance, maybe across the house.
Yeah. It's 30 feet between the globe and the model moon. If the Earth was the size of a basketball, 30 feet, which is pretty far. I don't know if it's across a house, but that's 3 stories up.
Yeah, that's a good way to put it. Yeah, 3 stories up. That's what gives you really good.
The moon is far.
Yeah. And okay, so then in that same relative system, where is ISS?
Yeah, so the space station is basically put your thumb on the globe, and your thumb is on Sacramento, and the back of your thumb, the thumbnail, is where the space station is.
Right.
It's like an inch above the globe.
That's insane.
Yeah. Yeah.
God. Yeah.
And you could fit every planet inside the distance between the Earth and the moon. Like Jupiter, Saturn, all of them. There's that good picture online.
Yeah. And it's not just every planet. It's Saturn and its rings.
Oh, I didn't know that. I actually would have thought not that, but that's crazy.
I'm pretty sure it's its rings too.
And there's still some room left over.